When you run an LLM, your GPU operates in two entirely different physical regimes. The moment a prompt hits the engine, you enter the prefill phase. Here, the GPU is happy. It is compute-bound. Because you are processing the entire prompt simultaneously, the tensor cores are saturated with massive matrix-matrix multiplications. The arithmetic intensity is high, meaning we perform a massive number of floating-point operations for every single byte of data we fetch from high-bandwidth memory. But the millisecond you generate the first token, the engine transitions to the decode phase. Now, you are generating tokens one by one. This is a memory-bound nightmare. To predict just a single token, the GPU must fetch every single weight of the model, plus the accumulated key-value cache of all previous tokens, from HBM into the local SRAM. The arithmetic intensity plummets. Your multi-teraflop tensor cores sit idle, starved, waiting for memory bandwidth. If you naively batch new incoming prefills with ongoing decodes, the heavy compute of the prefill delays the latency-sensitive decode steps of other users, causing massive latency spikes. To solve this, modern engines implement chunked prefill. Instead of processing a 4,000 token prompt in one massive compute burst, we slice it into chunks of, say, 512 tokens. We then co-schedule these prefill chunks alongside active decode steps in the same execution batch. This budget-based scheduling keeps the GPU's compute engines continuously saturated at optimal utilization without starving the memory-bound decodes, effectively flattening the execution profile and maximizing throughput. To understand why traditional batching fails at scale, look at how GPUs actually process LLM requests. If you batch two requests together, one asking for a simple yes and the other generating a 500-word essay, static batching forces the short request to wait. Even though the first request finished in 2 steps, its GPU memory and compute slots remain locked, idling, until the second request completes all 500 steps. This is head-of-line blocking, and it destroys throughput. Iteration-level scheduling solves this by shifting the scheduling boundary from the sequence level to the individual token step. Instead of waiting for an entire batch to finish, the engine evaluates the active batch after every single forward pass. The moment a sequence emits an end-of-sequence token, its KV cache is immediately deallocated, and its slot is freed. But the real engineering challenge is handling the phase mismatch when inserting a new request. A new request starts in the prefill phase, processing its prompt in a highly parallel, compute-bound operation. The existing requests are in the decode phase, which is memory bandwidth bound, generating one token at a time. Mixing them directly causes execution bubbles. To resolve this, advanced engines use chunked prefill. The scheduler splits the incoming prompt into smaller chunks, say, batches of 256 tokens, and co-schedules these compute-heavy chunks alongside the memory-heavy decode steps in a single iteration. This technique, sometimes called split fuse, balances the arithmetic intensity of the workload, ensuring the tensor cores stay saturated without starving the active decoding steps. It turns a chaotic, unpredictable queue into a continuous, highly efficient pipeline. Quantization isn't just about shrinking weights from FP16 to INT4 and getting a free 4x speedup. There is a hidden tax paid in two currencies: representation accuracy and hardware instruction overhead. When you scale LLMs past 6.7 billion parameters, emergent outlier features appear. A tiny fraction of activation channels, less than 0.1%, spike to values up to 100 times larger than the mean. If you apply a naive symmetric per tensor quantization, these massive outliers force the scaling factor to stretch, squeezing the remaining 99% of your normal activations into just 1 or 2 quantization buckets, completely destroying the model's perplexity. This is why we have to use mixed precision schemes like LLM.int or AWQ, which isolate these outlier channels in FP16 while quantizing the rest. Then there's the execution tax on the silicon. You might think storing weights in INT4 saves compute, but modern tensor cores do not actually perform mixed precision matrix multiplication directly on INT4 weights and BF16 activations at peak throughput. Instead, the GPU must pull the INT4 weights from high-bandwidth memory into SRAM, load them into registers, and then execute a series of bit shift and ALU instructions to dequantize those weights back to BF16 before feeding them into the tensor core. This register-level dequantization creates a massive bottleneck of non-tensor instructions and spikes register pressure, which can actually limit your warp occupancy. If your kernels aren't highly optimized to hide this dequantization latency behind memory fetches, you end up compute-bound on the ALU, completely wiping out the memory bandwidth savings you quantized for in the first place. Speculative decoding promises a free lunch. Let a lightweight draft model guess 5 tokens, then verify them in a single, parallel forward pass of the giant target model. But at scale, this setup hits a brutal optimization wall. The first issue is acceptance rate decay, which is driven by context length divergence. As the KV cache grows, the attention entropy of the draft and target models diverges exponentially. If your draft model has a 70% acceptance rate on short inputs, that can collapse to under 20% when generating structured syntax like JSON, where a single mismatched schema token invalidates the entire speculative sequence. But the real paradox lies in the hardware cost of rejection. When the target model rejects token 3 out of 5, we have to slice and roll back the KV cache. In a high-throughput continuous batching engine, this is highly inefficient. We must pre-allocate physical memory pages in the block allocator for the maximum speculation depth for every active slot. When tokens are rejected, we are actively wasting memory bandwidth allocating and then deallocating these virtual blocks. Furthermore, verifying those 5 tokens shifts the target model's execution profile. Autoregressive decoding is strictly memory bandwidth bound. But verifying a batch of speculative tokens increases the sequence length of the forward pass, pushing the target model into a compute-bound regime. At high batch sizes, the arithmetic intensity of verifying rejected paths saturates the tensor cores with useless work, meaning speculative decoding can actually deliver lower system throughput than vanilla autoregressive generation. When you scale LLM inference to multiple GPUs using Megatron-style tensor parallelism, you aren't just partitioning the model weights, you are sharding the KV cache itself. Take a model using grouped query attention running across a tensor parallel size of 8. If the model has 8 KV heads, each GPU stores exactly 1 head's worth of key and value vectors per layer. On paper, this is a massive memory win. Each GPU only allocates VRAM for its local slice of the history. But here is the mechanical bottleneck. While the attention calculation happens locally on each GPU using its sharded KV slice, the subsequent projection layer is sharded row-wise. To produce the final attention output, the system must sum the partial results from all 8 GPUs. This triggers an all-reduce operation over the NVLink interconnect for every single token generated, at every single layer. At batch size 1, this communication is fast. But as continuous batching pushes concurrency limits, we hit a brutal reality. The activations being transferred are tiny, just 1 token's vector per sequence, meaning we are completely dominated by interconnect latency, not bandwidth. The GPUs sit idle, stalled on the NVLink ring. This gets even trickier with multi-query attention, which has only a single KV head. You can't split one head across 8 GPUs. To make it work, you have to duplicate that single KV cache across all cards, completely wiping out your tensor parallel memory savings. This is why production engines carefully align group query attention head counts with the TP degree, ensuring the KV cache shards perfectly without triggering catastrophic cross-GPU memory replication or choking the NVLink bus. During the decoding phase of LLM inference, we face a brutal memory bottleneck. Unlike the prefill phase, where we process thousands of prompt tokens simultaneously, decoding generates exactly 1 token at a time. This means our query tensor has a sequence length of 1. Traditional flash attention parallelizes across the query dimension. When your query length is 1, this parallelization scheme collapses. Your GPU has over 100 streaming multiprocessors, but you are only utilizing a fraction of them because there are not enough query blocks to distribute. The rest of the hardware sits idle, waiting for the massive KV cache to be dragged from high bandwidth memory into SRAM. This is where flash decoding rescues throughput. Instead of parallelizing over the query, flash decoding partitions the KV cache itself across the sequence length dimension into smaller chunks, say, blocks of 256 tokens. We assign each of these KV chunks to a different thread group running on a separate SM. Each thread group independently computes the attention weights and the weighted sum of values for its assigned chunk. Crucially, because softmax requires global normalization, each group also outputs its local maximum value and the sum of exponentials. Once all thread groups finish, a final, lightweight reduction kernel runs. It takes these partial outputs, rescales them using the global logsum exp to correct the softmax denominators, and merges them into the final attention vector. By shifting the parallelization axis from the query to the KV cache, we maximize SM occupancy even at a batch size of 1 with long context windows. We turn a sequential memory read into a highly parallelized split-reduce operation, cutting attention latency by up to 10 times. When we scale LLM serving, we often stack optimizations like Jenga blocks, assuming they compose cleanly. They don't. Speculative decoding relies on a high acceptance rate, the target model validating the draft model's cheap predictions. But when you introduce quantized KV caches, compressing keys and values to FP8 or INT4 to maximize concurrency, you introduce quantization noise directly into the attention layers. This noise subtly shifts the target model's output logits. In isolation, an FP8 KV cache still generates coherent text because the argmax token remains relatively stable. But in speculative decoding, we are validating draft tokens against the target model's actual probability distribution using modified nucleus sampling. That tiny distribution shift from quantization noise is catastrophic. The draft model, running on a different precision or architecture, diverges. When the target model evaluates the draft's tokens using its noisy, quantized attention maps, the mathematical alignment breaks down, and the acceptance rate plummets. Now, overlay high concurrency via continuous batching. Speculative decoding requires validating multiple tokens at once, which inflates the KV cache allocation per step. Under heavy concurrent load, paged attention has to manage fragmented, quantized blocks. The overhead of dequantizing these KV cache blocks on the fly, combined with the memory bandwidth saturated by high batch sizes, completely erases your compute savings. Instead of accepting 4 or 5 tokens per step, your acceptance rate drops to 1. You are now paying the validation overhead of 2 models, but getting the throughput of 1, effectively engineering a system that is slower than baseline autoregressive decoding.